Okay. Let's talk. We'll talk through some things. Maybe when we take our break, we'll try this again in some other ways. Okay. But I find this is, and we did this for a reason, guys. And I will. Those of you that have had me before know that my favorite thing is basically to like convince you of something that you're wrong about, and then you try to sort of illustrate that in front of everyone else in class, which was sort of like an odd thing for me in 3813 when we did our anxiety stuff last week, 2 weeks ago. When was it? I don't even remember. It was like a week and a half ago. And like everyone in class, like, what are you anxious about? And they're like, failure and like, things in front of other people. And I'm like, okay. So, which I'm there with you. We're all afraid of failure. That's like, okay, we gotta talk about it. So I do this. I hope you guys will take it in the spirit of what I'm trying to do. Oftentimes, if you have a misconception, okay, and then you get proven wrong about that misconception in a kind of clever way or a way you weren't expecting, then it sticks with you, right? You'll always remember the questions you got wrong on the test, more so than the ones that you got right. So that's why I try to do that. I hope you all will take it in the way that the good-natured way that I intended. Okay, so we said, right, 3 fiber types or 3 general sort of human fiber types. Okay, slow twitch, and then fast twitch type A, fast twitch X. We originally, right, in the old way of doing things, it was just fast and slow. All we knew about was the speed of the myosin ATPase, okay, in the 1960s. That's all they could do. So it was fast and slow. And then as we got better at doing biochemistry, we figured out that the fast twitch ones come in slightly different flavors in that particular way. And so, right, so I will use them interchangeably. I will try to call them type 1 and then 2A and 2X rather than fast and slow, but that's going to be just kind of a thing. Hopefully you guys can kind of follow along in the midst of all of this. Okay. And so we can build these individual profiles. I actually looked back to see if I had any pictures of the old things that we did when I was a PhD student. And I didn't. But in the olden days, you would take a biopsy, you put this under a microscope, and you'd see these fibers, and then you would incubate them with some ATP to make the ATPase run, and you put them in, this is an acidic environment, and what you would see then is that like the type 2 fibers will look light when we do all of those. You can put them in a slightly less acidic environment, and they really look light. You put them in a basic environment, and then that's going to turn the type 1s. This way, how and why that happens is irrelevant to you guys. But what we would do is you would stain them, you would identify this fiber is this, right? This fiber is what they're calling a 2B, we would call it a 2X fiber. And then by having these little sections right behind it, you can line them all up, and then I can see this exact same fiber on consecutive slides. And one of them we look at the myosin ATPase speed. And the next one, we stain it for something from the Krebs cycle. And then the one after that, you stain it for LDH or an anaerobic. You can begin then to look at the same fiber and see what its metabolic characteristics are, how much glycogen it can store, how big it is, and you can learn stuff about them in that particular way. And that's how we have arrived at basically the things that we see in this sort of slow twitch, fast twitch 2A, and fast switch 2X, this kind of capacities and things that we're going to see. Okay. Very general. You guys were right on the button with all of it. Okay. Type 1 are the slowest twitch speed, which means if we give them one action potential, it will increase its force production. The slope of its increase in force is going to be not quite as steep, okay, as on the fast twitch ones. That's one way we're going to get those things. Okay, that's going to be another way we can look at this is to look at the conduction velocity of the motor axon. Okay, we also look at the size of the motor unit. We'll talk about motor units today. But in general, remember, a motor unit is one motor neuron, all of the muscle fibers it connects to. And in a motor unit, every fiber is going to have the same fiber. Okay, So we refer to motor units as a slow twitch or type 1 motor unit, right? Type 2A motor unit, 2X. And what we see, which we'll get into a little bit later on today, is the smaller the motor unit, the smaller the number of fibers connected to the nerve, to that alpha motor neuron, those tend to have slow twitch or type 1 fibers. There's some really important reasons why that needs to be. Okay. But you can characterize them based upon that. We can characterize them based upon how much or how many mitochondria they have, the density of the capillaries that go to them, the amount of myoglobin that's going to be in them. Generally, type 1s have more capillaries, more mitochondria, more myoglobin than 2A. 2A has more of those than 2X. Okay. The reason that I said that sprint speed is the thing we should ask everybody about is that myosin ATPase speed determines most of your sprinting speed. Okay. You can't change that with activity. That doesn't change no matter how much you train or anything else. Right? If you're fast, you're fast. If you're like me and you're somewhere in the middle, you get a little bit faster by doing weight training, working on your running form, and some of those things, but you're never going to be an elite sprinter if you don't have a lot of it. It's not. Okay? The endurance characteristics of all of these fibers, capillaries, mitochondria, glycogen stores, myoglobin stores, if you do aerobic training, you can get a lot more of all of those things in every one of your fiber types. Okay? In every one. So the endurance capacity tends to be somewhat genetically and type determined, but it's also really, really highly influenced by how active. Every one of you can be a much better endurance runner than you are right now if you'll just put in some time and train. I can make all of you better endurance runners. I probably can't make any of you much better sprinters. There's just no ability to go in this. Okay? As I said, genetically determined at birth. Okay? Your fiber type percentage is roughly the same in every muscle in your body. Okay? Roughly the same. Your diaphragm is generally the slowest muscle in the body, has the highest percentage of slow twitch fibers. Right? You contract your diaphragm a ton, right, in your life up until now. Your diaphragm ever been fatigued? Sure. Hope so. Okay. Right? If you've ever been like, ooh, I just can't breathe because my diaphragm is like burning. Happens very rarely. Right? Very slow twitch. The next slowest muscle is probably your soleus and other postural muscles. You use them all. Okay? Probably 80% of you guys in the room are 60-40, fast to slow or slow to fast, one way or the other. Right? The vast majority of people in the population are somewhere 60-40, one way or the other. Very few of you are going to be 70-30, one way, much less like 90. Okay? But to be an elite sort of long distance runner or an elite sprinter, you probably have to be one of those outliers that's 90% direction. Lots of athletes and folks that do middle distance stuff in track and rowing and all of that can be 50-50. Be somewhere in the middle. Last point. This was a thing I think Claire emailed about. We cannot change ones into twos. No matter what you do. Run all you want. Sprint all you want. Not changing. We can't change twos into ones. What we can change, the only thing we really can change, unless you are sort of very, very, very super inactive, is if you do any kind of activity, your 2X's will turn into 2A's. Okay? 2X's will become 2A's. Whether you walk, run, lift weights, whatever it is that you're doing, if you're just not a couch potato, you're going to drive your 2X's to be 2A. 2X's are like tank or something, and they're fuel efficient. It's not adaptively good to have 2X fibers, unless for some reason all you want to do is like one vertical jump. Okay, so the sort of evolutionary thing that happens is we go from X to A, we keep the vast majority of the strength and the speed component, but we gain a capacity to have a lot of endurance or a lot more endurance. That may seem counterintuitive. Okay? That's what's going on. That's what's going on. Questions about all of it? I think I was like 72% slow. My dad's a marathon and a high school football coach. He's an interesting sort of trial and error. And I desperately needed to be just a little bit faster. I could have been a better football player. Last. We talk about VO2 max, like I showed up and had to run a bunch in my VO2 max. My mom was also a runner. So I have a lot of mitochondria. I showed up in grad school and had a VO2 max of 60 and hadn't done much in a while, which we'll see. Like now it's like 25, so way out of shape. So I was fairly genetically blessed to be a pretty good endurance athlete. Some of you guys are in the same boat, right? Some of you guys, that's what it is. The real weird question is, some of you all said, well, I run a bunch, or it was Zach that said, what are you good at? If I run and I sprint and I do really good at sprinting, then is that self-selection? You have a lot of 2s, so you're going to be better at sprinting, so that's what you're going to do is more sprinting. The person that has a lot of type 1s, so the thing you're good at is endurance events, and so then you practice the endurance events and then you sort of self-select yourself out in that way. If you could know what you had or what your kids were going to have, would you want to sort of shove them towards one sport or the other? There are companies, 23andMe will try to tell you genetically if they have the genes that might make them muscle mass responders if they do resistance training. Okay. Of course, if you do that, they're selling your genes and all of your information to, I think it's Merck or somebody. So, cautionary tales. Do you want to know the answers? All right. These things, we hit this. Yep. Okay. I will just point out some of this, like on this deal. You guys, I'm not going to ask you questions about exactly how many muscle fibers tend to be in a motor unit of flow twitch or 2A or 2X. I just have the numbers in there to illustrate in some ways to you kind of where they're going to fall relative to each other. Okay. Again, the contraction speed, like 150. This is what I think we're going to talk about later today, called rise time. And this is in milliseconds. You don't have to know that type 1 fibers have about 100 millisecond rise time, and 2A and 2Xs are about twice as fast at 50. I just want you to appreciate where they fall relative to each other. Okay. Okay. There's a lot of details that matter. Those aren't the ones that we're going to concern ourselves with. Okay. Shortening velocity. I like this. I borrowed this slide, or I should say I stole this slide from my master's thesis advisor. So it's very old. And what I like is the sort of way we can illustrate here. We have type 1 fibers, type 2A, and type 2X fibers. And what it's trying to show in sort of the purple and the 2 yellow bars is the capacity of those fibers per their size, okay, to make ATP. And it really is to make ATP with aerobic metabolism from your mitochondria, okay? And then in the hatch, the kind of red striped bars, it's going to show, if you contract them repeatedly, about how much relative ATP they use during prolonged kind of repeated contractions. And so what you can see from all of this is in many ways kind of the relative fuel efficiency or ATP efficiency of these individual fibers, where in our type 1s, we're relatively close, right? We're relatively close in the amount that they can make aerobically and that they can use if you're driving them as hard as they can. 2As, you can see they may actually be able to have, because they're bigger, have more mitochondria in them if you're really, really active than type 1s, but they have more capacity to make, but they use way more. They're way less efficient because their ATPase is less efficient. And so they're going to have less of an endurance capacity. And then the 2Xs, I said, are like a tank, right? They can't make very much and they use a shit ton. Okay. And so the ability to kind of match these two things together is going to determine your endurance and how well you can actually kind of keep doing things. Okay. I like that as kind of a visual representation. Okay. Questions? Comments? Concerns? Nothing? Okay. We need to sort ourselves in some other way now. Right? No? Okay. So we talked about fiber type. Let me show this last little bit because I think it's sort of interesting. I didn't bring the book, it's in my office. So these are taken from a paper that was in a book. That's the reason that I am an exercise physiologist right now. These are data from the 1972 men's Olympic distance team. Ladies, y'all didn't have an Olympic distance team in 1972. They were worried your uterus would fall out. That's a literal thing. They did not let women run the marathon until 1980s. They thought it would mess up your uterus. You wouldn't be able to have kids. Okay? So, yay, the patriarchy. But what we have here is slow twitch fiber percentage, okay, listed from, these are the guys that were on the distance team. Slow twitch fiber percentage, this is slow twitch fiber area in square micrometers, fast twitch fiber area, right? The percentage of all of their muscle area that is slow twitch, and then it's the activity of LDH, which is an anaerobic enzyme, and then SDH here. We don't need to worry about what the phosphatase was. And they have, here are the Olympians. Here are sort of good collegiate middle distance runners. And by good, I mean, like they got to run. I think they were from like Ball State's middle distance team. And then they have some untrained, relatively untrained men. They have VO2 max guys and a bunch of other things from these guys. But I just want you to see that the Olympic distance runners were about 80% slow twitch. The collegiate middle distance runners were about 62, and then an average untrained guy was a little under 60. That was right there. But look at the difference here. We have, let me look at these things. This Tuttle fellow was 98% slow twitch. Okay. And then we had somebody here who was only 50% slow twitch. So some of this, and these guys ran various distances. Some of them ran a mile, some of them ran 10,000 meters, some of them ran the marathon. There's more data on their best, like mile time, 5K time, marathon time. But I show this just to say that fiber type isn't everything, right? There's this wide variety in all of these things. And just because you have a huge number of slow twitch fibers doesn't mean you're going to be an elite Olympic distance runner. And just because you don't have a lot doesn't mean that you can't. And so I just think that's always really interesting to look at the differences. But in general, elite distance athletes tend to be more slow twitch than the general public. Okay. All right. Now, on to the next. 52. So let's talk about the nervous system. I said yesterday, right, that we had Ty get up and play. Dr. Black says, and he could move and do the things that I was asking him to do, but only on command. And so we talked about what's going on sort of in the muscle from an anatomical standpoint yesterday. We're going to start now talking about what's the nervous system. What is that connection from your brain out to those individual muscle fibers that we learned about yesterday? So we'll talk about the anatomy of all of that. Then we'll get into basically all of these signaling events that occur as we go from you think about contracting to actually contracting, okay? And then stopping that contraction and then doing it again, okay? So remember, we tend to break the nervous system up into peripheral nervous system components and central nervous system, okay? Generally, the peripheral system is going to be things just like what it says, out in the periphery. You have afferent receptors in your skin that sense temperature, touch, chemicals, a whole host of different things that are going to be out there, right? They're going to send information back into the central nervous system. And so a lot of our stuff here in the central nervous system, what we're going to really get into is going to be brain, or specifically motor cortex, okay? My brain anatomy is very poor, but we're going to do motor cortex stuff, spinal cord, okay? And then from the spinal cord, we're going to talk about special neurons in the spinal cord called motor neurons. And then they're going to shoot off a connection. It's going to be an axon. It's going to come out of the spinal cord. And it's going to come out and essentially connect the brain to individual muscle fibers. Okay, so we'll get ourselves through basically what's going on in the central nervous system. We'll talk about how we get a signal down through the axon, some specialized structures, what happens, where it gets really close and essentially contacts the muscle fiber. And then we'll put all of that together to figure out all of these steps. And then maybe you'll be like me and you'll be astounded that you can ever move, ever. Right? You're like, there's like 27 steps to go from thinking about contracting to getting a contraction, much less doing it over and over again at just the right amount of force, and stopping at just the exact right time. It really all kind of blows my mind. Physiology is a trip. Okay, so the brain and the spinal cord are connected to skeletal muscle via this hub in the spinal cord that we're going to call collection of neurons. They're called alpha motor neurons. Okay, alpha motor neurons. Here you can see kind of a cartoon of an alpha motor neuron. It sits in the spinal cord, and I'll show you guys kind of where, talk about why they are where they are in a minute. Okay, so you have about 450,000 motor neurons in your body. You have roughly 250 million muscle fibers. Okay, so obviously there's way more fibers than there are motor neurons. So every motor neuron is going to have multiple connections and connect to multiple fibers. But every fiber in your body is only connected to one motor neuron, only to one, right? If it wasn't, then there'd be all kinds of problems. You'd have all kinds of problems, okay? We'll talk about motor units in just a little bit, which is going to be the motor neuron and all the fibers that it goes, okay? Okay. That's the general initial setup, all right? So let's talk about what a motor neuron, or really in some ways any neuron, would look like, and then we'll work our way back kind of into the spinal cord and the brain, and then we'll work our way down the axis. So, cartoon of a neuron, okay? This area here in the middle is called the cell body. This contains the nucleus. It contains several other structures, but the real job here in the cell body is to make all of the things that that nerve needs to be able to send signals. So it makes neurotransmitters. Okay? It makes proteins. And there are these really cool things that are called molecular motors or walking proteins that are like myosin, but they run stuff down from the cell body all the way down the axon. It's going all day long. Okay, you're making acetylcholine here in your spinal cord, and then you're walking it down your axons all day long to get it out to the neuromuscular junction. Okay, so that stuff goes on there. Around the cell body are these little finger-like projections that are called dendrites. Okay, dendrites are like nerves for a neuron, but their job is to sense things from the environment around that cell body. Okay. If Destiny had dendrites coming off around her, and I was like, waving at her, doing things, it gets picked up here. you have to remember that in the spinal cord, it's just a collection of all of these nerve cells. It's just a collection of neurons. And so these dendrites are going to pick up signals from other neurons that are adjacent, things called interneurons and stuff that are really, we're going to get into neuroscience and stuff if we do that, but it's going to pick up stuff from the environment. Okay? They're really important to get a signal from the brain actually to here. We need the dendrite. Right? Then we have the axon, which you guys think of as a nerve when you go in and dissect and like into an anatomy class, right? When you guys would see a nerve, what you think of as a nerve is really a bundle of axons. That's what it is. Okay, right? Like my ulnar nerve is down here. You hit your funny bone. There's the nerve that runs kind of right there. What that is, what you see as a nerve under a microscope is just thousands of axons all grouped together. Okay, so cell body is in the spinal cord. Axon leaves the spinal cord and then goes all the way out down to the muscle that motor neuron is connected. So you've got things coming out down here at like S1 and S2 that are going all the way down your legs to your toes, right? To the muscles that control your toes. Okay? Or you've got things from up here at like C6 that are coming down and controlling your thumb or your bicep. So as you can imagine, axons are long. They can be very, very long. Okay? Around the axon, we're going to do this because the axons being long is actually a problem. Around the axons, we have a layer of what is in essence fat that is called myelin. Okay? Myelin comes from specialized cells called Schwann cells. And myelin it's a lipid. That's why I say it's fat. Okay? But it's a lipid layer that wraps itself around the axon. Okay? And by having myelin, it allows us to transmit electricity or an action potential down the axon a lot faster. Okay? There are several neuromuscular disorders in which we lose myelin on our axons and people start contracting very slowly. It's much more difficult to get an impulse to go. Okay? And I'll show you guys a better picture of this coming up, but the myelin is not one big long continuous sheet that wraps around the axon. At regular intervals along the axon, there are going to be places where there is no myelin. And those are going to be called nodes of Ranvier. At the nodes of Ranvier, there's a large collection of sodium and potassium channels. And that will become really important when we talk about generating action. Without the nodes of Ranvier, without the myelin, our ability to quickly transmit a signal from the brain to the spinal cord, from the motor neuron out to the muscle, slows down dramatically. Okay? It slows down dramatically. Okay. So, we hit most of these kinds of things. So, this is kind of I like this picture, kind of a little bit better 3D representation of what dendrites look like. So, here's your cell body in the middle. You've got one axon coming out, and there's all of these little thin hair-like projections coming off in sort of all three dimensions off of there that are going to gather information from the surrounding environment. Okay. Now, most of you probably know this, but we're going to go over it again. Motor neurons have very specific and very precise locations in your spinal cord. Okay? So a couple of ideas to start with. All of the motor neurons that go to the same muscle are going to be next to each other in your spinal cord. Okay? So all of the motor neurons that say go to my bicep are in the same place. All of the motor neurons that go to my quads, my knee extensors, are in roughly the same place. Okay? We'll talk about why that's beneficial in just a second. But it breaks down mostly like this. Here we have cervical vertebrae, right? So head, skull here, cervical vertebrae, thoracic vertebrae, lumbar vertebrae, sacral vertebrae, like this. Okay? And you guys don't have to know the precise location at which vertebrae, which things are going to come from. And I'm not going to ask you that much. But you can see here, right, from about C3 through C8, we have the vast majority in our cervical vertebrae, the vast majority of our upper body muscles. And it tends to roughly correspond to the closer to your head, the higher up in the spinal cord. Right? Diaphragm, though, is at the very, very top. You need your diaphragm in order to breathe. We lose our connection to our diaphragm. You can lose your connection to your hands, and it's not going to immediately kill you. But if you lose your connection to the diaphragm, the closer up here, the less chance there is of getting sort of an injury. That's why that's going to go that way, right? But here you've got deltoids and biceps at C5, wrist extensors and things at C6, triceps at C7, and muscles tend to be at about C8. Any of you guys that work in rehabilitation clinics or have ever been to rehab, if you have injuries at various locations, you get numbness, you get tingling, you have weakness and things, we can essentially trace back to an area in the spinal cord where there might have been an injury or compression or something based upon sort of peripherally what our symptoms are. There's relatively less sort of muscle innervations in the thoracic vertebrae. Internal and external intercostals, abdominals, right? Rectus abdominis, obliques, and those kinds of things are going to be there. And then most of our lower body muscles are going to be down in the lumbar spine. Okay. So hip flexors at like L2, knee extensors at L3, ankle dorsiflexors, so the TA, right, are going to be here. Plantar flexion is all the way down potentially at S1. So your gastroc and soleus and things are going to be down there. And then most things sort of in the sacral vertebrae are not really going to be that kind of motor dependent type of thing. But you've got bowel and bladder function and things that are going to be down. Okay. So what you get then is all the bicep motor neurons are all in the same place, right? Like they're all going to be at C5. Okay. Why might that be a good thing? What's that good? All in the same. Emily, you have any thoughts? Why is it good?
I feel like this one used to be. I feel like maybe for surgeries.
Okay. So let's try to imagine a scenario. What would happen if I had some bicep motor neurons at, let's say, where they're supposed to be at C5? Then I have some way down at, let's just say, S1. And my brain says, I need to do a bicep curl, right? It's Tuesdays. The bros are probably doing curl. It's probably curl day, right? So we're going to do curls. I got to pick something up. And I got some of my motor neurons that are about here, and the rest are way down here. And I really need to turn all of them on at the same time to pick up that really, really heavy, dumbbell. Why would it be a problem if some were here and some were way down here? Anybody guess? No one try to help everyone out? How would that be a problem? Slower. What do you mean it's slower?
Yeah.
If they're in different places, then the ones that are closer to the brain are going to fire first. Then that's got to travel all the way down here. And so they're not all going to be able to kind of fire and depolarize at roughly the same moment. So there may be some delay that may cause a lack of precision in the amount of force that I get and some herky jerkiness, right? To use my lovely Arkansas terms, herky jerkiness about kind of what we're doing. So in that way, having all of them in the same place is potentially good because then you can fire all of them at the same time if you need to. Or if you're doing something where you have to hold something for a long period of time and you're not using all of them at once and you got to turn some on and some off as you're going along, they're kind of all in the same place and you can maintain force a little bit better. What's the downside, Riley? We're all in the same place. What's bad about that?
If you got injured, they're all gone.
I get injured, they're all gone. Okay. And so one of the things that we did when I was a PhD student is we worked with people with spinal cord injuries. And you would always ask them, like, where's your level of injury? And, they would have very, very clearly, just figure out where it was. And some people would have, right, they would have triceps, but not biceps. If they could do this, and they couldn't bring their arms back. They would have a little bit because, right, they had a cervical injury above C7. Right? And that's the problem, is everything below a level of injury is gone. So it's kind of some give and some take that we're going to get. Having seen stuff like in a cadaver, I'm amazed every time that we fall over, we don't just like rip our spinal cord in half. Every time that you do anything, your nerves don't just like all sort of pop out and do a bunch of things. Because they seem really, really delicate, but they are yet very, very sort of well protected and kind of robust. Okay. This just tries to show sort of a rough way of approximating, right? Like they're all going to kind of be in this sort of cylinder, right? Like if this is at L4, and then, maybe we would be like L5 at about right here, and S1 kind of right in there, that you can see like they're going to all kind of sit in the midst like all of this. Okay. So what we also need to talk about ever so a little bit is the idea that we have dorsal and ventral sides of the spinal cord. Okay. And so the ventral side is the inside, the side facing sort of your stomach and intestines and all of those things. And then the dorsal side is going to be on the back, right? So all of the alpha motor neurons are going to be located in the ventral, what's called the ventral horn, and gray matter of the ventral horn, which is going to be right here. So then nerves will leave, axons will leave out of here and come out of the spinal cord and into a nerve bundle, and they're going to run adjacent to what we call afferent, or things that bring sensory information in, which are going to come in the same nerve bundle. They're going to bring stuff in, they're going to branch, and they're going to come in and connect in through the dorsal side. Okay. So we're going to talk about, maybe today, probably tomorrow, a thing called sensory motor integration, where as information from your body comes back into the spinal cord, it's going to come in on the sensory side, on the ventral side, on the dorsal side, and it's going to have, through the dendrites and things, it's going to signal to these motor neurons here and help you adjust and maintain force production and kind of let you know what else. Okay? That's all the neuroscience we're going to do, I promise. Mostly because that's all the neuroscience that I know in the midst of everything. Okay, so this is just showing kind of the other deals. We talked about the axon. We talked about all of this. Okay, so a couple of things I want to point out. I got a different cartoon. It's going to come down here. Cell body, dendrites, axon, nodes of Ranvier, myelin, and then these things down here on the very end. Okay, they're called synaptic knobs. Okay, these are going to be, as the axon gets out and it gets very, very close to the muscle fibers, it splits. Okay, and even though it thins out on the very, very ends, there's going to be these little bulb or knob-like structures where we're going to try to increase surface. And I'll show you guys some blown-up pictures of that in the coming slides. Okay, you have, and this is fascinating in some ways, a series of what are called neurofilaments and microtubules. You guys remember talking about those in maybe in like freshman biology or anything, talking about microtubules? Maybe? No? Remember mitosis? Those things, right? Anaphase, we're pulling apart and stuff. Okay. Anyway, this is a scaffold. Microtubules are going to be a scaffold that runs all the way down the axon. And then we have things that are going to walk down the microtubules to bring us neurotransmitters. The cool thing about this is that by having microtubules, by having these nodes of Ranvier, central nervous system structure, so neurons, if they die, they're gone. They're never coming back. Peripheral damage, though, damage on an axon, damage here at the end by the synaptic knobs, because of the microtubule structures, because of the nodes of Ranvier, we have some level or some capacity to actually regenerate axon. Okay, because of that scaffolding structure, we can build stuff back along there. But if you get neuron damage, once the neuron's dead, it's dead. It's gone. You're born with all the neurons you're ever going to have. You're born with all the muscle fibers you're ever going to have. Imagine that. Little tiny baby, right? Little baby. Same number of fibers as that person will have when they're an adult. There you go, 14 times that size. You have all the neurons you're ever going to have when you're born. So, stuff again that kind of blows my mind. All right, let's talk about the Schwann cells. And at these nodes of RON-VA, we have very, very high concentrations of voltage-gated sodium channels. We remember voltage-gated yesterday? We talked about the dihydropyridine or something. Remember voltage-gated? What does that mean to be voltage-gated? There has to be a gradient, okay, where it flows, Callie. Exactly. Opens or closes due to a change in membrane. To get an action potential, which we will talk about later today, you're going to have to open voltage-gated sodium channels, let a bunch of sodium come in. Sodium is very positively charged. As it comes in, the inside of the axon is going to go from negative to positive. Voila, that's electricity. That generates an action potential. And so what happens is by having all of these things at the nodes, then you're going to get action potential and it's going to go from node to node to node. Okay? It's slightly more complicated than that, but for our purposes, that's going to work. The process of the action potential moving from one node of RON-VA to the next, sort of down this axon very quickly is something called saltatory conduction. I do need you guys to know that. Saltatory conduction. Okay? If you have multiple sclerosis, if you've had Guillain-Barré syndrome or something, then you may lose some myelin and you lose your ability to have saltatory conduction, and conduction velocities will slow down. Movement speeds slow down. Movement strength goes down. Okay. So I promised you guys this, and we'll take a little break. This probably looks better on your computer than it does up here, but high resolution picture of what we're going to call a motor end plate, which is another way of terming what's also called the neuromuscular junction. Okay. Here we have axon, or a bundle of axons running here. We're then going to have these branches coming off of those axons, coming down each one of these. You can see the stripes. That's an individual muscle fiber. So it branches off. It comes down here very, very close, and then it splits into the little finger-like structures that have the knobs on the end. This is going to make a neuromuscular junction. This is the connection from the nervous system to an individual muscle fiber. From the nervous system to the muscle fiber. So this is how we're going to tell that fiber, how the brain tells this fiber, hey, generate force. Go through the cross-bridge site. Okay. You will note, right, coming out of the same axon, there's going to be several places where they're going to split. They're going to go to relatively adjacent muscle fibers that are going to be here. So that's what we call this. These things used to be called a motor end plate. We mostly call it the neuromuscular junction. Now they're used relatively interchangeably. Sometimes people will mean, well, the part of the axon and this is the motor end plate. The junction is actually sort of right down underneath the motor end plate, the individual little folds and structures where we're going to release acetylcholine and where we're going to bind acetylcholine, which I'll show you guys in the coming slides. But that's kind of what all of this looks like. Okay. Let's take about a 5-minute break. Okay. And then we can continue on. Okay. Okay. So what we're going to do now is we're going to get into, and this is going to be a place where you're just going to have to memorize some stuff, into a lot of the cellular level details, the receptor level details of how the nervous system connects, and I'm going to say that in quotes because it does not physically touch, but it connects and will signal from the nervous system to the muscle fiber. Okay? So what you see here is called a neuromuscular junction. This is what is occurring underneath that motor input. Okay? Here is one of those synaptic knobs. It's sometimes an old neuromuscular physiology textbook called a bouton. So you might see that referred to in some places. I may accidentally call that, but we kind of call it a synaptic knob now. So axon has branched, it comes to here. This is going to kind of bulb its way out like a light bulb to increase surface area. Okay. Here, the part here on the bottom, this is the sarcolemma. You will note that in the sarcolemma, there's going to be folds. Okay. The sarcolemma folds for the same reason the axon side or the nervous system side bulges out. It increases surface area. Why is your small intestine 27 feet long? Because it folds a lot, right? You can have lots of surface area to absorb things. You just imagine if there's like 27 feet of small intestine like wrapped up in here. Okay, that's what's going on. Having more surface area is really, really, really important. Okay, it costs an axon or it costs the nerve a lot of energy to make acetylcholine and move that acetylcholine from the motor neuron all the way down the axon. Okay, so imagine the thing that's like a micrometer across, and it's got to cover, like 4 feet. It's a very, very long way. It's like us running from here to Kansas City. It's a long way to go. And so what we want to make sure that we can do is have lots of area so we don't have to release very much acetylcholine. And when we do release it, that we're very efficient at capturing it and having it bind onto its receptor on the muscle side. Okay? Because it's very costly to make more and to move it all the way down. Okay? So, there's not a physical connection, it just gets very close. On the sarcolemmal slide, we call this sort of pocket right here, kind of immediately under. This is called the primary neuromuscular cleft. The primary cleft. The sort of finger-like folds that press down into the sarcolemma here are called the secondary neuromuscular cleft. Okay. In the cleft on the sarcolemmal side are a bunch of receptors. And they are receptors for our primary neurotransmitter that's going to induce our signal. And that neurotransmitter is acetylcholine. Okay, I will abbreviate that as ACH on most of the slides from here on out. Okay. So what we get is an action potential travels from the central nervous system through the motor neuron down the axon until it reaches the synaptic knob. Okay. When it reaches the synaptic knob, what's going to happen is there are additional receptors up here kind of on at about 10 o'clock and 2 o'clock if this was a clock face. And they are voltage-gated calcium channels. The action potential comes down. It is going to open or activate those voltage-gated calcium channels, which means calcium is going to move from outside of the axon here to the inside. That influx of calcium signals for the acetylcholine to be released. What you see here on the bottom near the sarcolemma, these are vesicles. They're little small bubbles. In that bubble is a bunch of acetylcholine. Okay? And so what happens, the calcium comes in, and then through a signaling process that we're not going to get into, it tells these vesicles. So a vesicle is a bubble. On the outside of the bubble is a lipid bilayer. It looks just like the cell membrane here. The vesicle will come to the edge, and then it integrates itself into that membrane, and then it just releases or dumps out its acetylcholine into the primary and secondary neuromuscular cleft. Okay? That acetylcholine, hopefully then, will bind onto these acetylcholine receptors on the sarcolemma, and then that will lead for a chain reaction of additional things that we'll talk about in the slides that will get an action potential on the sarcolemma. Okay? So we're going to go from an electrical signal in the nervous system to a physical signal of calcium, a second physical signal of acetylcholine, and then we're going to go back to an electrical signal on the sarcolemma that's an action potential. Okay. So this is as good a place as any to talk just briefly about why we signal the way we do. Okay. What's the usefulness of electricity as a signal over a physical signal? Anybody want to guess? Why electricity? Right. That's right. It's really fast. Okay. Really, really fast. So from the brain through the nervous system or the central nervous system side of things down the axon, really, really fast. Okay. That's good because if I can jump out of the way of something, I put my hands hot, I got to pull it away. Electrical signals give us speed. The physical signals and those things are going to give us, in some ways, a little bit more control over the tightness of our binding and ability, because electricity is sort of all or none, right? It's either on or it's off. These physical signals give us the capacity to say, I got a little bit of acetylcholine, or I got a lot of acetylcholine, right? Or I got a little bit of calcium, or I got a lot of calcium. It's less of an issue here, okay? But that physical signal becomes really, really important when we get down to the sarcomere level. That calcium from the sarcoplasmic reticulum level becomes really, really, really important. That's why we signal in different ways. Again, form or structure imparts function. Okay? Imparts function. Okay. Now, we talked about everything that's on here except for the basement membrane. Okay? You're going to have basement membrane both on the inside and the outside of the sarcolemma, right along here in the primary and secondary cleft. I told you guys yesterday the basement membrane is important for structure. Okay? It's also really important from a function standpoint for signaling from the nervous system to a muscle. Embedded in the basement membrane is a special enzyme called acetylcholinesterase. Get ready to spell that one on the quiz too. Okay. Acetylcholinesterase. You guys will learn. If you don't know what I can't spell, right? I have many academic gifts. Spelling is not one of them. Drives my wife crazy. Drove my mom crazy when I was little, but I'd be great at math, do chemistry, I can do calculus, I can't spell to fucking save my life. Okay? Acetylcholinesterase. What acetylcholinesterase does is it detaches acetylcholine from the acetylcholine receptor. Okay? That's the off signal. That's the off signal to stop a muscle contraction. Okay? Or to at least stop the nerve telling the muscle to contract. And so it is located inside the basement membrane. So if you damage the basement membrane and you do something, you lose acetylcholinesterase, you may lose an ability to turn off a muscle contraction once it starts. Okay. We will do an assignment where I give you guys some spider and snake venom type of things, and several of them work by either blocking the acetylcholine or they block the acetylcholinesterase. So you get bitten by a snake and you can't relax your muscles. If you can't relax a muscle, then it contracts until it fatigues and it runs out of energy, and then you can't move. then the snake comes and eats you. So not a great way, not a great way. But that's where the basement membrane and the acetylcholinesterase become really, really important. Okay, so we covered all of the rest of this. Okay, now, and I always struggle with where to put a motor unit, but I put it at the very end here where we've already talked about it. So we've kind of covered on one individual motor neuron, down its axon, right, to its neuromuscular junction, and kind of looked at those structures and how it connects to a muscle fiber. Well, there's going to be multiple connections that are going to branch off of that axon. So there's multiple neuromuscular junctions that are going to all go to different fibers that are going to come from the same motor axon, the same axon which comes from the same motor neuron. That grouping of one neuron and all of the fibers it connects to is called a motor unit. Okay, it's a motor unit. Motor units are the most important functional collection of things in the neuromuscular system. Okay, and we'll see a little bit more today and especially tomorrow why that's going to be the case. But motor neuron, axon, all of its fibers. Okay? We're going to talk about how the nervous system talks to or connects and tells the muscle to contract on a motor unit by motor unit basis. So this, in many ways, is the functional unit of the neuromuscular. Okay. In some instances, if I got you to generate the smallest amount of force possible from a muscle, you would turn on one motor unit and one motor unit only. Okay. Most of us can't get that sort of precise with those things. That's how we're going to control. We use motor units to control how much force we get by turning on more or less motor units to get more or less of a muscle to contract. Okay. Unsurprisingly, I'm sure to you guys, not all motor units are the same. Not all created equal. We have the number of motor units per muscle varies greatly. Bigger muscles tend to have more motor units, right? They got more fibers, they need more nerves to connect, more neurons to connect to. And then within a muscle, there are going to be some motor units that are very small. 10, 15, 20 muscle fibers that are connected to one neuron. And then they may range all the way up to some very, very large motor neurons. Very, very large motor units that might have several thousand fibers connected to one. Okay. So here would be a small motor unit. This might be a large motor unit. And then there might be some that are even bigger. Okay. And so because the central nervous system signals with electricity, when the motor neuron generates an action potential, every fiber downstream that connects to that neuron is going to contract. So when this one contracts, a small number of fibers contract. When this one contracts, a much larger number of fibers contract. Okay? More fibers, more cross bridges, more force. Fewer fibers, fewer potential cross bridges, less force. Okay? So our ability to turn on the correct number of motor units for the amount of force that we need is a really complicated process. One that we have a lot of adaptability. We'll talk a lot about that. Okay. Does this make sense? If this doesn't make sense, tomorrow is going to blow your fucking mind. Okay, so we have to get this. Going once, going twice. Danny, you got this? You're good? Sure? Okay. All right. That's how this is gonna get set up. Okay. Now, we're going to talk. Let me see how much time I've got. Yeah, we'll be okay. So we're going to sort of leave that sort of stuff there. And we're going to talk about sort of basic, like neurophysiology. Okay, this is very, very basic human phys of the nervous system, because I know you guys have already had it. You probably had it multiple times, but it's really important. And so I want us to go back over it again one more time. Okay. And that's the idea of what is an action potential? How do we generate action potentials? What do we need out of cells to be able to generate and move action potentials? Because action potentials are unbelievably important for how the nervous system sends signals, and then how the muscle also sends signals. Okay. So an action potential is a brief electrical signal. Okay. A small shock. Right? Claire turns around and shocks at it. Okay. Would have been easier if it was the winter and we had some park, right? You do one of these shocks. When I say brief. Propagated, you're going to see the word propagated a lot. Propagated means it moves. Okay. We could propagate an action potential from me to Braden to Carly to Hannah to Kiara. We would just turn around, you guys would just high five our way back. That means it's moving. Okay. Now, the electrical signal is actually, electricity is generated when we flip the charge from one side of a membrane to the other. Okay. In order to do that, we have to have different charges on different sides of the membrane. So the membrane we're talking about here is going to be the cell membrane of neuron, the axon, the sarcolemma. The difference in charge from inside to outside is called a membrane potential. Not all cells in your body have a membrane potential. But cells that do have a membrane potential are capable of generating and transmitting action. So cells that have a membrane potential are said to be excitable. Nervous system tissue, neurons and their axons are excitable tissue. The muscle fiber membrane, sarcolemma, is an excitable cell or an excitable cell membrane. Okay. So, in order to be excitable, as I said, we have to have a resting membrane potential, and we have to be able to maintain that membrane potential by having what we call concentration gradient. Okay. This is why we make you guys take chemistry. Okay. A concentration gradient means there's more, and in this instance, there's more ions that have positive or negative charges on one side of the membrane versus the other. So if there's more positive on the outside, there's more negative on the inside, that means there's a potential, there's a difference in charge from inside to outside. Okay? We have to have these things. I also should have put on here, in order to generate action potentials, that membrane must be somewhat or relatively impermeable to those ions that make up the concentration gradient. If they're readily permeable, stuff just moves back and forth until it reaches equilibrium, and we get to never have those things. Okay? So we'll talk about what those ions are and how we deal with this in the coming slides. Okay? Okay. Now, let's just say here is a neuron. Here's a nerve cell. Okay? Here's the membrane of that nerve cell. Here's the cytoplasmic side. Here's the extracellular side. Right? What you can see then is we have a higher concentration of negatively charged ions on the inside of that neuron and a relatively higher concentration of positively charged ions on the outside. Okay? And so that creates a difference where there's more positive out, more negative in. And that creates this, what we call a resting membrane potential. This membrane is impermeable right now. These negative ions can't go from inside to out. These positive ions can't go from outside to in to try to equilibrate, okay, our potentials. You guys remember hypertonic, hypotonic, right? Diffusion, all of these things. Stuff wants to be at equilibrium, right? And so if they can freely move, then they'll get to a place where they're exactly equal on both sides. That's not where we are right now. So not all cells have a resting membrane potential of minus 70 millivolts, but we're going to use that as sort of our example of what's going on. So in this nerve cell, there's more negative ions inside, so our resting membrane potential is said to be minus 70 millivolts. It might be minus 60, it might be minus 55, it might be minus 72. The number isn't of super great importance, but it's just relative to outside. Okay? So we now have two things here. There's a difference in charge. There's also a difference in the concentration of, let's say, the blue negative charge things are chloride ions, and the positive sort of red charged ones are sodiums. You guys remember that from chemistry? Sodium has a +1, chlorine has a -1. Yeah. Okay. They like to bind to each other and make table salt. So that's what's going on here. All right. Now, this is all set up, so our nerve is ready. It can generate an action potential if it gets the right signals. Okay. So one of the reasons that we're able to generate an action potential is that we can switch, okay, and open up channels or pores that are going to allow for the movement of those sodium ions or those chloride ions, chlorine ions, okay? And so what we've got here, here's this relative sort of concentration inside of a nerve cell, okay? Remember, we've got a negative charge inside, a positive charge outside. We've got a bunch of sodium outside, very little sodium inside. We've got a bunch of potassium inside, very little potassium outside, okay? I know that I told you guys those negative charges might have been from a chloride ion. They're actually not, so don't worry about this. What I want you to know from these two things is that sodium is high outside, low inside. Potassium is high inside, low outside. These are the two really important. Okay. How do we get things to be that way? Two things. One, our membrane does not normally allow sodium or potassium to move across the membrane. And two, in order to generate these concentration gradients, we have to have things called ion pumps. An ion pump is going to forcibly take sodium from inside the cell and pump it or move it to the outside of the cell. It's going to move it out. Okay. And that helps us create this concentration gradient. That costs us some energy. It's called active transport, but that's going to be a good thing, right? So we can close things, pump sodium out, pump potassium in, and generate our gradients. Okay? All right. So when we want to get an action potential, there's going to be this sequence of things that's going to happen. And so initially what we're going to get is a thing called a graded potential. A graded potential is just tapping the person next to you, right? Low, 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 tapping. It's not annoying yet. You don't want to turn around and, sort of swat them with the backhand on the shoulder and be like, hey, leave me alone. This is a small input. Imagine what's happening is I have a neuron. I have an alpha motor neuron in the spinal cord. I am picking up signals from the dendrites. Those signals are initially what's called a graded potential. It's a little bit of a signal that says, let a little bit of sodium in, let a little bit of sodium. Let's move our membrane potential in a positive direction, minus 70 towards, say, minus 30. Let's move it up a little bit, okay? So it all starts with the graded potential. If you get enough of a graded potential, okay, it lets enough sodium in and it moves our membrane potential to a value that we call a threshold potential. in my example, minus 70 at rest, gradient potentials are pushing us toward our threshold, which we're going to call minus 55. Again, 70 and 55 are not exact numbers. They're just kind of relative things that are, okay? Gradient potential gets me to threshold. Once I reach threshold, boom, action potential will happen. There's no turning back at that point, okay? We've jumped off the high dive at this point. Gets to here, at threshold, at about this minus 55, it triggers the voltage gates on the vast majority of the sodium channels that are going to be in the membrane of that neuron. Sodium channels open, sodium moves down its concentration and its ionic gradient from outside to inside. As those positive charges come in, the inside of my cell becomes more and more positive. That is what we call a depolarization. Sodium channels open, sodium rushes in, we go from a negative membrane potential to a positive membrane potential. That's an action. That's depolarization. Okay? Boom, it's fire. Right? We're going to get to a place then, this all happens very, very fast. We're going to get to a place relatively quickly where it spikes, and then we're going to start shutting everything down in effort to go back down here to get back down to resting membrane potential so we can generate another action potential. So this process is called repolarization, going from positive back to a negative membrane. In this area here, what is happening is the voltage goes positive. That triggers the closing of our sodium channel. Sodium channels close. We're going to then keep open our potassium channels. And so potassium then is going to go from inside the cell to outside. So we're taking positive ions from inside the cell, they're rushing out. That means we're becoming less positive or more negative inside the cell. It's going to repolarize us here. We generally get a thing called hyperpolarization. It's an overshoot, okay? Where as we're repolarizing, we actually become a little bit more negative than we need. We overshoot resting potential. This is called hyperpolarization. And then in a very brief amount of time, that will then get rectified right back to our resting. Okay. Until we get back down here, we cannot have a second action. Don, stand up. Touch your toes. Okay. Maddie, how many action potentials do you think it took Don to do that? How many is he sending in order to be able to just bend over and touch it? What do you think? 5, 10, 1 million, 1 billion? You don't know? Okay. You think it's a lot? Yeah. I don't know either. The answer is a lot. Okay. So how long did it take Don to do that? Like a second or two? Okay. In that amount of time, Don, you can sit down. Thank you. In that amount of time, he generates probably thousands, if not hundreds of thousands of actions. Okay. So you depolarize, repolarize, depolarize again. This is the only way the nervous system can send signal. It's either on or it's off. And so its way of modulating the extent that it's on is by the number of action potentials you get in a period of time. So you get like one poke per second. All right, fine. But if it needs to be more than that, then it's like tap, 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 tap. Okay. So we need to be able to do this really, really quickly. And there's a couple of other things that are happening as we're repolarizing that I want to mention. Okay. So we show this in discrete steps, but it all happens really, really fast. You don't have to know this. I'm not going to make you draw it. I bet you had to know it and draw it in human physiology. What you see here is you are drawing the curve. The red curve is the action potential, so that's membrane potential. And then the two purple curves are measures of what we call sodium conductance and potassium conductance. And this, the conductance is basically how much of this is moving for a period of time. And so what you can see is that early on, the potassium moves, or the sodium moves really, really quickly, and then it comes back down. The potassium opens at the same time, but it moves much slower until sodium begins to fall. Potassiums actually work better at this kind of mid-range membrane potentials. And then it's going to take a little bit of time to kind of repolarize ourselves. Okay. So that's just these things laid over the top. I just think they're very illustrative if you're a visual person to try to understand what all is going on. Okay. So this is the same sequence of things. Okay. We're going to get opening of sodium channels. Sodium comes in, action potential. Okay. Then as we generate an action potential in one piece of a membrane, then that causes an action potential in the adjacent piece of membrane, and it starts to move itself down those membranes, and that's how electricity is going to move. During the repolarization process, okay, then we're going to close the sodium channel. We're going to open the potassium channels. Potassium comes out, and then we're going to run the sodium potassium pump to blow the sodium back out, bring the potassium back in, restore our gradients, and we're ready to have an action potential. All of this happens in just fractions of milliseconds. Okay, it's really, really fast that this is going to happen. Okay, two things I want you to know here: a thing called an absolute refractory period and a thing called a relative refractory period. Okay, there is a very short window of time during repolarization where no matter what the gradient potential the nervous system sends to that neuron, you will not be able to get a second action. Okay, that's called the absolute refractory period. You cannot get another one right now, no matter what we do. Okay, that is this area in sort of reddy peach here. Okay, the absolute refractory period covers the period of time when the sodium channels are open. As long as the sodium channels in the membrane are open, you cannot get a second action. It does not matter what you do. Okay? Once the sodium channels have closed, okay, we have mostly repolarized, been able to repolarize and restore some of our ion gradients down here. Then we reach what's called the relative refractory period. The relative refractory period tends to cover the time from the closing of the sodium channels until we can return our hyperpolarized neuron, where it's overshot that resting membrane potential and become more negative. We can get it back by running the sodium potassium pumps back to its normal resting membrane. Okay. During the relative refractory period, we can get a second action potential. It's possible, but because we're farther down, we're more negative, there's farther to go to reach that threshold. So you need larger or more graded potentials coming in. You need a bigger signal. Okay? You got to really want it in order to be able to go in and get a second action potential in the relative. Okay? Questions about it? I assume you guys have heard of those two things before. Hey, were you okay?
There's a spider in the corner, and it can't kill it.
Okay. Do you need assistance? Do you want to just get up and move? Okay. We'll call somebody after class. But... Okay. I would not want to be. I don't like spiders at all, so that is no problem for me. If you want to. Okay. It's okay. Never had that experience in class before. No, it's okay. Fine. Okay. Okay. So this is the absolute and relative refractory period graph laid over the top of where the action potential is, and then the sodium and potassium sort of conductance curves all together. And so this just illustrates to me in the absolute refractory period, we're still moving some sodium. So until the sodium gates close completely, we're always going to be in the absolute refractory. Okay. That's the idea there. This will make more sense tomorrow when we talk about how we use the number of action potentials that occur right on top of each other to modulate force production. Okay, this is just propagation and it moves in one direction. So everybody do this. Everybody put your finger down here where your ulnar nerve should be. Ooh, that's okay. I don't know why that makes me weaken my knees, but I can rub it right there. Okay, ulnar nerve. Now imagine you came to my lab. Okay, I can put an electrode sort of on one side of your elbow, put a second electrode right down here underneath, like on the head of a pin, and I can shock that nerve or that bundle of axons. That's right. Okay, because the axon is an excitable membrane, if I depolarize a spot out here in the middle, which would be like right here. If I start the depolarization right here under your elbow, the action potential will spread in both directions on that nerve. Okay, it will go down to my fingers, it will come up to my shoulder, and it would eventually then run back to the motor neuron. Okay, because the membrane is excitable, it will spread in every direction. This will be important when we see what happens at the neuromuscular junction with the sarcolemma. It's going to spread in 3 dimensions. However, in the nervous system, we don't start things in the middle. Okay? If we did, you'd never be able to move because you just send signals in both directions in the nervous system. It would be bad. So when it starts at the motor neuron and it moves down, let's just say, or out to my hands, only coming this direction. It only moves in one direction because it depolarizes, okay? And then it's going to go one way. It cannot go backwards because the piece of membrane immediately behind it is in the absolute refractory period. And so it can only move in one direction when it starts at a location like the neuron, okay? Or if you started at the neuromuscular junction, it would do the same thing. But we don't ever start the nerve. So we're only going to get one-way traffic. Okay? You come to my lab, we can get two-way traffic in the nerves, and we can make some weird things happen if and when we want to do it. Okay, but that's why, again, the absolute refractory period is really, really important. Okay, so we talked about this. This is just sort of the cartoon way to show all of this. Action potential comes down the axon. It moves to the bouton or the synaptic knob. It opens these voltage-gated calcium channels. Vesicles integrate. Acetylcholine released. It binds. Then, at the acetylcholine receptor, that generates an action potential. So now we get an action potential on the sarcolemma. And on the sarcolemma, from where it starts, it can go in 3 dimensions. It can go in every possible direction. Okay. So if it starts in this one place right here at the top of the marker, it will spread out from there in every possible direction. So 1 or 2 connections is usually sufficient to get an entire muscle fiber to depolarize very, very quickly. Okay, because it will travel across sarcolemma. That happens, you get an action potential. Technically, the action potential on the sarcolemma is called an in-plate potential rather than an action potential. Because we're fucking scientists and we're never happy and we're calling something that's got a one name something else to make ourselves feel special. And then we'll turn off or use the acetylcholinesterase to turn off our signal there. Okay. All right. You know what? Let's stop here. Okay. We'll pick up tomorrow with excitation, contraction, coupling, And then we'll talk about actual production. So the quiz tomorrow will be over the things that are in the fourth set of PowerPoint. Okay, the muscle contractions and control of force production PowerPoints. Okay, all right. Thanks, guys. Have a good rest of the day. What do you want? Is that good or bad? Look at the big stuff. You didn't have to wonder. We'll see how we do with all of this. You know, tomorrow we can play. We just take practice signal again. Somebody can play an action. Run around the room, like high five each other and do things. We gotta get up and move around and try to illustrate things like that. Okay. I did, Don.
What's it make sense?
So-
You have to get it.
What? We'll be here at all of them. You take it and put it in my, I'll take it and put it in my office. So like, you get it early or something on Monday.
I'd go with that one here.
I'll be out. I won't be even back until.
Yeah.
Then can you just come and take it before class on Tuesday? Let's see what it is. I should be here by like 9 or so. You want to come in? If you.
Yeah, we like-
Yeah, it's 2 hours and 15 minutes, so. We ran it at like 10 or something. We'll give you to like 12:30 and then try. Try. You want to come a little early, like at 9:30, because you want to take it. I'll be.
For this process, right?
Send me an email on Monday to remind me, just that way I can make sure that if for some reason something comes up, like I don't know, I was fucking sick or something, I can leave a test with.
Okay, so this is all like,
Actually, you
Yeah.
can come Tuesday morning with somebody's.
okay, so this is like an entire like running process. Yeah. That's crazy. No, but that's like a really good way to write it out.
Okay.
And the arrows. This is like, I don't feel like I've ever gone this in depth or anything. Like, I took physiology, but it was like, I don't know, like, it was like a.
Y'all gonna draw everything out
No, you
tomorrow.
need it.
I was telling Callie,
Yeah, no, it's.
we're gonna line everybody up and we'll be an action, but we'll like high five our way around the room and somebody can, I'm serious, and then I have a.
It's really good.
My guess is that I asked my 3813 class to do just what you've written down on their first test last semester, and they all fucking bombed it. And we'll ask Ty about it tomorrow. But let me see, is it just like step by step, everything? Oh, yeah, that's exactly right.
All of that, though, you don't need to know anything. Maybe. Okay.
No, we're gonna talk about what kind of receptors we actually have in those things. Very, very close.
I didn't realize it was, this sounds stupid, but like, it all. Yeah. Goes together. I thought these were just like separate, like, things in my head, but I guess it's an entire, like.
In all, every time
I
you
looked
move.
at the picture.
Yeah.
Even if we're going to the crossroads, oh, this is that. But it's like.
Metabolism is blow your mind. Because every metabolic process in your body is going on simultaneously, right? It is not this weird, like, oh, it's this, and then it's this. And when that's all going, then we do this. No, it's all at the same time.
Yeah.
And it's a really difficult thing to kind of wrap your head around.
Yeah.
Okay.
Thank you.
All right. Bye, guys.